Tristan completed his PhD in Engineering and Technology at the Catholic University of Louvain, Belgium, followed by the postdoctoral fellowship at the Albert Fert National Center for Scientific Research, France, and then he returned to his alma mater. He's currently a Marie Slowodska-Curie Action European Research Area postdoctoral fellow at the Institute of Systems and Computer Engineering, Microsistemas and Nanotecnologias of Portugal, and he's working on 3D interconnected magnetic nanowire networks. And today he will present his work titled Neuromorphic Weighted Sum Operation using Magnetic Skyrmions. So Tristan, please go ahead. Thank you very much.
Thank you very much for the introduction, and thank you very much for the invitation to this conference, which I find is a very great concept. So I'm very glad to participate. So in this presentation, I will show you how we can perform the neuromorphic weighted sum operation in hardware using magnetic skyrmions. The goal is to perform the weighted sum operation is one of the main mathematical operation of a neural network. So neural networks typical architecture is shown here on the slide, and it's composed of two main parts. One is the synapse, which makes the connections between the neurons and also holds the part of the memory. And the other part is the neuron, which do the processing and sum all the signal coming from the synapse. This performs the weighted sum operation, which is mathematically written as such, and then does apply a non-linear function, which is the activation function on the result of this weighted sum to give an output that is then sent to the next neuron in a synapse. And the synapse and the neurons are in an architecture with different layers. We have the input layers here when we get the input signal, then a lot of hidden layers and output layers. And to perform very complex tasks, we need deep neural networks, so a lot of hidden layers between the input and the output layers. Currently, when we do artificial intelligence, all these neural networks are done in software, and we use conventional computing hardware for the computation. But this is not really efficient because we have these conventional computers with the separation between the memory and the processor. So in the field of neuromorphic computing, what we're trying to do is to have an hardware that does directly all this operation to be much more efficient. The complexity is that we need a lot of synapse and neurons. And here I would like to show that skyrmions can be used to perform the weighted sum operation. So this operation here of summing all the signal coming from different synapses. So magnetic skyrmions, they are magnetic texture, circular magnetic texture, such as the one drawn here in the slide. And the main properties that we're going to use here is that they behave like a particle. So they are non-volatile, they are stable at room temperature. If we nucleate skyrmions, they will remain there. And because they are particle, we can count them. So we can nucleate a given number of skyrmions and then count how many skyrmions we have. And then we can perform operation on those skyrmions. And it has been shown that we can engineer the magnetic multilayer to stabilize magnetic skyrmions in those magnetic multilayer by playing with all the interfacial and bulk magnetic properties of the multilayer. And then we can fully control those skyrmions electrically. So we can nucleate them, we can move them, detect them, then annihilate them all fully electrically. So they are quite interesting for devices, computing devices and memory devices. And here we're going to use this particle behavior and the fact that we can count the particle to perform the weighted sum operation. So the weighted sum operation is schematized here on the left of the slide. So we have different inputs, electrical inputs that will be sent, and each of these inputs will be multiplied by weight to give this Y value here. And then we will sum all those Y value to get the final output. And the way we will do this with the skyrmions is sending electrical pulses through tracks that can hold skyrmions, and that will nucleate at a given location, at the nucleation site, a given number of skyrmions. Then we can move those skyrmions in the detection area here and measure electrically the number of skyrmions. And we will have the weighted sum if the number of skyrmions that is nucleated at each nucleation site is proportional to the input and the weight of the track. So we want here linearity. And if at the end the electrical output that we record depends on the total number of skyrmions that is nucleated in each track. So we need to be able then to have an output that reflects the sum of the Skyrmions in each track. This draws some parallel with how the weighted sum is performed in our brain, where we have voltage spikes that arrive through the synapse and that will nucleate some vesicle with neurotransmitter that will accumulate at the neuron. And then when a given number of neurotransmitter accumulated, we have an output spike that is emitted through the neuron. So here, the Skyrmions plays the role of those vesicle with neurotransmitter that and that is nucleated and accumulated at the neuron. The synapse is played by this Skyrmion hosting tracks, and the neuron is played by the electrode that we use to detect the voltage. So for the proof of concept devices, what we use is a track made of cobalt, aluminum, platinum repetition. So you have here the stack that is used, and in this stack, we can stabilize at room temperature Skyrmions of about 200 nanometer in diameter. That you can see here in the CARE microscopy image. And we nucleate the Skyrmions from a notch that is defined by lithography. This is our nucleation site here. And then the neuron is the output electrodes, which is drawn in red in the image, and it's made of tantalum, thin tantalum electrodes that is contacted only on the edge of the track, so that we can see here the Skyrmions in the middle. All the measurements are performed at room temperature, and this is just a proof of concept devices, and the goal is to integrate this in an array such as the one you can see on the right. So now when we pass some electrical current in this track, what you can see is that we nucleate the Skyrmions from the notch and only from the notch, and then the electrical current moves the Skyrmions in the track in this oblique direction, which is due to the Skyrmion Hall angle, and here was about 15 degrees. So the Skyrmions are moving in the track, and they can cross the tantalum electrodes to be measured here at the Hall cross. Why do we have only nucleation of Skyrmions at the notch? Is because we have a higher current density at this location. So the notch is used actually to have a local point where the current density can be much higher than in the rest of the track and can be above the Skyrmion nucleation threshold, while the current is below this threshold in the rest of the track. And then if we report the number of Skyrmions in the track as a function of the number of pulses that we apply, we see this linear behavior, which is what we were looking for. So we have a linear relationship between the input parameter, here, the number of pulses that we apply, and the number of Skyrmions that we have nucleated. So this is one of the two things that we needed. We needed this linearity between the input and the number of Skyrmions. And the weight of the track here is the slope of this graph here, and in this case, for those particular parameter, the slope is about 1 Skyrmion per pulse. So then, if we change some parameter, for instance, if we change the current density, or if we change the pulse duration, we see that we can change the slope. So we can adjust by changing the current pulse input parameter. We can select the slope that we want. The interesting thing here is that this is not a deterministic nucleation. That means that we can have a slope that is less than 1 Skyrmion per pulse. We have actually a probability to nucleate the Skyrmions, and if we apply a pulse, we could have the Skyrmion nucleated or no. This probability can be tuned. So this is so we can have this in this case here, for instance, less than 1 Skyrmion per pulse that we nucleate in the track. So we can have very low number of Skyrmions nucleated with a large number of pulses, or we could also tune the parameters so that at each pulse we nucleate a large number of Skyrmions. For instance, here it's about 4. If we report now the slope, so the number of Skyrmions per pulse as a function of the pulse duration, we see that this is linear. So that means that instead of using the number of pulses as the input parameter, we can also use the pulse duration. That will also work. So we could work with only one pulse and different duration. So this is another input that we could use. But if we report this as a function of the current density, we see that we have more of a quadratic behavior. And this makes sense because here in this case, the Skyrmions are nucleated by thermal effect, and the thermal energy is proportional to the square of the current. So we have this quadratic behavior here that we can see on the slide. And that means that the current density is an improper input parameter. We cannot use it as the input parameter because we don't have this linearity between the input parameter and the number of schemons that we would nucleate, which is a drawback because the current density would have been the easier parameter to use in a network. Now, if we decide to use as an input parameter the number of pulses, the equation is the number of schemons in the track is equal to the weight of the track times the number of pulses that we apply, and this weight is, as I said, the slope here, so the number of schemons per pulse. Now, if we change the out-of-plane field that we apply to this track, we see that we can change this slope. So this means that the out-of-plane magnetic field that is applied can be used as a way to tune the weight of the track. This is a volatile way of controlling the weight of the track, because if we remove the field, we lose information of the weight. This is not an ideal way of having the weight of the track written in the track. It's written in an external parameter. However, what is interesting is that we have a very linear behavior between the field, the out-of-plane magnetic field, and the number of schemons per pulse, so the weight. That means that this linearity is interesting because it's easy to control. We want this linearity between the parameter that we use to control the weight and the weight. This is interesting for future development of writing the weight into the magnetic properties of the track by, for instance, magnetoionics, because we have this linear behavior between the magnetic field and the number of schemons per pulse. So this is about controlling the number of schemons in the track. Now we need to be able to detect electrically this number of schemons. And the way we did this is using anomalous Hall effect, which gives us a linear probe of the schemon number. And to measure this anomalous Hall effect, we sent a DC current in the track, and we measure the voltage at the edge here of the transverse electrode. And the trick is that we use high resistive tantalum electrode. So high resistive meaning that the resistance of this tantalum electrode is about 100 times larger than the resistance of the schemonic multilayer. And with this, we can measure the anomalous Hall effect. So this is by sweeping the field here and measuring the Hall voltage. We see that we can have this probe of the out-of-plane magnetization of the track. And why do we need this high resistive tantalum electrode? Is to avoid having a drop of current at the Hall bar. If we just make a Hall cross made of the same material of the schemonic multilayer, what happens is that the current density can drop here because it can enter in the Hall cross. And this would mean that because the schemon move due to the current density, that the schemon would reduce their velocity or stop at the Hall bar. So here what you can see is that because we have much higher resistance in the electrodes, in tantalum electrodes, we avoid this drop of current density at the Hall bar, and the schemons can cross the Hall bar without slowing down. So there is no reduction in the schemon velocity here. Another interesting thing is that this allows to reduce the sneak path. If we consider now an arrays of those devices, the sneak paths are the current paths that are not desired. If I apply a pulse like this in an arrays, there is the green arrows is the current path that is desired when the input just goes through the track, but there's this sneak path, this alternative current path that goes, for instance, like this, or in any other direction, like this. And if this is much higher in resistance than the track, we can expect that the sneak path will be reduced. So now, when we apply the current, we start to nucleate the schemons at the notch into this detection area here. And if we report the schemons, the number of schemons that is observed by Kerr microscopy as a function of the number of pulses applied, you see that this is the blue dots and they increase with the number of pulses. And if we, in the same times, measure the Hall voltage, we see that it matches very well the number of schemons in the track. So here there's 10 measurements with no schemons to have the baseline. Then we start applying pulse, increasing the number of schemons, and then we erase all the schemons by applying an out-of-plane magnetic field that is large enough to erase all the schemons. saturate the track, and we recover here the initial hole voltage. Then we can change the parameters, so we have more Skyrmions, and we see that we still have about 22 nanovolt per Skyrmions. And then we can also change the magnetic field, and it's the ratio is still about 22 nanovolt per Skyrmion. So this shows that we can count the number of Skyrmions using the anomalous Hall effect. And one thing also that we can do is, instead of erasing all the Skyrmions with magnetic field, we can electrically reset the system. So we apply positive pulse to nucleate the Skyrmions and inject the Skyrmions in the detection area. And then we can apply negative pulse to push the Skyrmion back to the notch where they will be annihilated and have no Skyrmions in the detection area. So we can have an electrical reset of the system. Now what we wanted to do is to demonstrate the weighted sum operation, so be able to sum the number of Skyrmions in two parallel tracks. So we build a device with two tracks that are parallel and one single tantalum electrode that contact both of the track. And if we measure, if we inject a DC current only in the first track, we can record the anomalous Hall effect of this track. And if we inject a DC current to the second track, we can extract the anomalous Hall effect of the second track. And what we see is that because this track are made of the same materials, and they're actually not identical because they're defined by lithography, but they're really similar. We have the same amplitude of an anomalous Hall effect. And then if we apply twice the current in parallel in the two tracks, what we see is that the output is the sum of the anomalous Hall effect in track 1 and track 2. Now we can use a BIST to inject Skyrmions in the first track. So you can see here in the Clara image, and we can we see that the anomalous Hall effect that we record at the edge of the device increases following the number of Skyrmions injected here in the first track. And then we can inject Skyrmions in the second track, and you see that we continue to increase the anomalous Hall effect at the edge of the devices, and that it actually follows the sum of the number of Skyrmions in both of the track. And then when we apply a magnetic field to reset the system, we recover the Hall voltage at saturation. So this shows you that we can measure electrically the weighted sum of the number of Skyrmions that is nucleated in the two track here of these devices, and therefore perform the weighted sum operation with magnetic Skyrmions. This device is scalable, so we can have more inputs and outputs by using a crossbar array geometry, such as the one here shown on the graph. So we can have more track in parallels and then stack neurons also in the transverse direction to have more inputs and have more outputs. And one interesting thing also is that here we've used anomalous Hall effect, so it's a very low output signal, but we could use magnetic tunnel junction with tunnel monitor resistance voltage, and therefore have a much larger output signal that we can measure. And here in this work, for instance, they demonstrate that they can read the number of Skyrmions in a MTG using a tunnel monitor resistance. So this could be implemented in such arrays to record to measure the sum of the number of Skyrmions with much higher output signal. And one interesting thing also in using tunnel monitor resistance is that the activation function, so the nonlinear activation function, could come for free if we have a large enough tunnel monitor resistance. Therefore, it means that the voltage would be nonlinear but monotonous with the number of Skyrmions. So we directly have all the mathematical operation needed in the neural network. Another thing that could be improved is to improve the nucleation mechanism. So here we've used electrical current to nucleate the Skyrmions by heat effect. And this is not very efficient because this consumes a lot of energy during nucleating the Skyrmion by heat effect. And also we have this nonlinearity between the current density and the number of Skyrmions. So one thing that would be very interesting is to have another way of nucleating the Skyrmions that will be with either current or voltage, and we could have a linearity between this current density or the voltage and the number of Skyrmions. And therefore, this would be quite interesting because then we would have a compatibility between the input and the output. See that here in the demonstration, the input is a number of pulse and the output is a voltage. But if we want to build the neural networks, we need the output of one layer to be the input of the next layer. So therefore, it would be interesting to be able to use this voltage that is measured here as an input for the next layer. And if it's, for instance, a voltage gate control of anisotropy, if we use voltage gate control of anisotropy to nucleate the Skyrmions, the VCMA nucleation, then we would have an output that is a voltage and an input that is a voltage as well. So we'd have compatibility between the input and the output of successive layers. So this is something that would be really interesting to add in this device. Just a quick word about the energy cost of the operation. It has been shown notably in this work here that if we use voltage control, so VCMA nucleation of the Skyrmions, we could have a very low energy for nucleation, one Skyrmions, about 20 picojoule. This is and it could be even below. Sorry. So now in our work we have about 20 picojoule, but it could be much below using voltage gating nucleation. It could be below 150 joules, so not so far from the energy for nucleation vesicle with neurotransmitter in the brain. Of course, also this energy will depend on the precision that we want and the weighted sum operation. So you can see that if we want some very high precision in the weighted sum, so for instance 100%, the energy goes to the infinite. But if we accept to have some imprecision due to the Skyrmion release probability, then we can reduce this energy. But this is not the precision of the final operation of the task. This is the precision on the weighted sum, and this error is acceptable in big networks that can absorb this error and in the network. So in the brain, actually, the vesicle release probability is quite low, as you can see here, and the values that we extracted in our device is about 0.6, which is about the same, as you can see here. So this is just a little comparison with how the brains work. One interesting thing also is to have non-volatile change of the weight by writing the weight in the track instead of using an external magnetic field. So here we've shown that we can tune the weight of the track by tuning the external magnetic field, but this is volatile. So if we remove it, magnetic field, then we lose the information. So one thing that will be needed if we want to build a full neural network with this concept is to have a way to tune the magnetic properties of the track in a non-volatile way, a reversible way, and this can be done through magnetoionics, so moving the ions in the multi-layer to be able to change the magnetic properties. For instance, in this work here, they demonstrated that you could, through magnetoionics and moving the ions, you can tune and have all the states of the magnetic properties, and this could be used in our devices as well. Notably in the system, so the platinum cobalt aluminum system, we demonstrate that you can, so here it's for 5 repetition, so 5 repetition of platinum cobalt aluminum. We demonstrate that you can tune through magnetoionics the properties of the top cobalt layers, and that this, so it's about here 1/5 of the anomalous Hall effect that is tuned through applying successive negative and positive voltage. And if we compare the gated area here for negative voltage with the S-grown area, we see that we changed the nucleation. So the nucleation is favored in the S-grown area and not in the gated area. So we've been able to demonstrate that we can tune the nucleation of domains, but those domains can be transmitted from one area to the other. And also you can see clearly that the domains have different sizes. So we can control the domain nucleation through magnetoionics in these devices. This is the conclusion. I've shown you here in this presentation that we can control the Skyrmion nucleation and the motion with current pulse using notches, that we can detect them through anomalous Hall effect without perturbating the Skyrmion motion, and that we can measure through anomalous Hall effect the sum, the sum of the electric signal from 2 parallel tracks, and that we can use magnetoionics to have a way of having a non-volatile and reversible tuning of the magnetic properties of the track. With that, we can have all the basic brick to develop fully electrical devices with all the operation in a crossbar array, such as the one shown here. Thank you very much for your attention.
Yeah, thank you very much, very much, Tristan, for your very nice presentation. Has anyone any question in the chat? Yeah, Giovanni, you can unmute yourself and make the question by yourself.
Hi, thanks for the very nice talk. I would have a question. Can you go to slide 15, please? Okay, the first question is, why do you saturate your signal here at some point? Like, it looks like the whole voltage signal is saturating. Is it because you are not nucleating anymore, or because it reaches a threshold where the signal cannot increase anymore?
Yeah, so we start to increase here the number of skyrmions in the detection area, but the detection area is finite. It's this square here. So at some point we nucleate and move the skyrmions, and at some point they start to get out of the detection area. So when we inject new skyrmions, there are also skyrmions going out of the detection area. So actually there's a plateau in the measurement. We could continue to inject skyrmions, but then they would get out of it. So the new skyrmions would get in the detection area, and the other skyrmions here would get out and annihilate here at the edge of the track.
Okay.
So we have a finite detection area, so there's a limited number of skyrmions that we can inject in this area. It's kind of this concept.
Okay, but then it's not the limited amount of, like, then you might say that for each of the 3 current density, you have different densities of skyrmion in the detected zone, right?
Yes,
because
exactly.
the plateau is always at higher voltage,
because
which is okay.
Actually for low current density, we would have only one skyrmion nucleating, so you would have like a queue of skyrmions going from a line of skyrmions going from here to here. So the density of skyrmions that you can have is, I mean, you see how they are spaced like this. So it would be like, I don't know, 6 or 7 skyrmions, for instance. And then when you start to increase, then you have 2 skyrmions nucleate one next to each other, and then more and more. And then here you can see that they're really packed. When we nucleate a lot of them at each step, and so we can pack a lot of skyrmions. So the plateau changes, but the plateau comes more from the fact that we inject skyrmions, they reach the detection area, and then at some points they filled all the detection area and start to get out of the detection area.
Okay, understood. But when you don't apply a pulse, the skyrmions stay there. They don't move, right?
Yes, exactly. Okay. So here, just to get an idea, each measurement takes a few minutes actually, because so we inject the pulse, then we have to stabilize the focus to get the image. So this takes some time. We stabilize the focus in Y, X, and Z direction. We take the image, and then we record in DC the whole voltage. And the whole voltage is a very low signal, so we need some time. So we actually do kind of a delta measurement. So it takes also some time to measure. It's not like a very fast measurement with this technique. Yeah. So we average over some time. But during all this time, the skyrmions are static.
Maybe it's then easier if you make it with TMR. Yeah, looking forward.
Yeah.
Thanks.
Of course, I mean, easier to make it, no, because it's harder to have measurements in the out of plane direction, which is one of the things doing this with TMR is that now everything is planar, so it's very easy to contact, it's easy to fabricate it. If you want to have MTGs, then you have detection you have to make the contact in the out of plane direction. This complicates quite a lot the fabrication and everything. But the output would be much better, yeah.
Great.
Thank you very much, Tristan and Giovanni.